Everyone doing okay?
Yeah.
Yeah. So let's see. Let's see how many of you were able to turn in the test. I haven't looked. So let's see. All right. Good, good. Okay. All right. So, yeah, how did that go? A lot of work, huh? I told you it would be. Tried to warn you. Let's see, I'm going to close it out here. So, all right. Any questions on that midterm? I mean, I don't think I can go through a problem, a lot of problems in detail, but I can give like any basic answers.
Is the answer for number 13 kind of just a rule, or is that just a fun coincidence?
I think the answer might, well, I can't share the answer because I have at least one student who had something come up and it's going to turn in late. So I can talk to you individually, but it should be a numerical, there's a numeric answer.
Yeah, I'm saying, was the answer like a rule of math, or was it just an interesting coincidence?
Maybe an interesting coincidence. Yeah. I will give partial credit for your work. I'm being asked that on the chat. So yeah, I mean, that's why I want to see your handwritten work, so I can give you partial credit in case things didn't go right. I can at least try and follow what you were doing. So give me some time to grade that. I had kind of I don't know, I've been having some computer issues, and not all of my OneNote notebooks, but a lot of my OneNote notebooks that I thought I had locally were on the cloud, and I can't get to them anymore, and they're not showing up on my OneDrive. So I don't know. I just figured this out today that I got a problem. So I'm working on it, but I'll get those graded as soon as I can. I've got a lot of other things going on, so just be patient. And we are going to continue. We are going to start 11:7.
I have a question.
Yes, go ahead.
Will there be an answer key or something for us to go through to see where we went wrong, or will you do?
Well, what I'll do is I'll grade it and I'll send it back to you graded, and then wherever I mark off, you just kind of want to look at maybe what happened, and then I would prefer if we meet and do like a Zoom session where we go over your test.
Okay.
It's kind of one-on-one.
Okay.
I don't like to put answer keys out for this class, because every time I put an answer key out, that means I have to make a new test for the next semester. And that, these tests, as you can see, I mean, I have to actually think through these problems before I make them. I can't just, it's not like a quadratic equation where I can just change numbers and everything's okay. So yeah, I'd rather just meet, talk about it. Okay, anything else? All right, so we are going to start 11:7. We're actually almost done with chapter 11. Believe it or not, we've kind of moved through this quickly. But on the other side of the coin is that we still have to do chapter 12 and chapter 13. So we're coming up on the halfway point of the material. All right, so 11:7. The whole idea here was to eventually be able to figure out the maximum and minimum values of a function. Just like we did in calculus, try and find these peaks and valleys of a curve. Here now we have a surface, and we're trying to see if we can use what we've learned to find the maximum and minimum values. So I would suggest that you review Cal 1, sections, chapter 4, section 1, and chapter 4, section 3. Now, I'll kind of explain to you what those chapters were about, just briefly. One thing we had, and you had to use this on the midterm, this was actually part of what you had to know to do the midterm, is that if you're given a function on a closed interval, then we should be able to find we can find these local maximums and minimums, but we should also be able to find the global max and mins. On the entire interval, we should be able to find the highest and lowest point. And to do that, we use what's referred to as the closed interval method. And in short, what that was you would take the function, you would take its derivative, you'd set it equal to 0, you take the derivative, figure out where it's undefined. Whatever x values give you 0 for the derivative, or whatever x values make the derivative undefined, what you do is you would take those x values, whatever they are, there may be more than one, okay? And you take those answers and you plug them into the original function. And you see what the function spits out, like what the y values are. And then you also take the two endpoints and plug those into the function. And you just compare all of them. And the biggest answer you get would be your max, and your smallest that you get would be your min. And that's what you learn in Cal 1. It's called the closed interval method. Then in 4.3, you learn, okay, well, what if you have a curve where you don't have an interval? So it keeps going maybe forever in each direction. Here you can't necessarily always talk about a global max or a global minimum, but you can find the local maxes and mins. But to do this, it's different than the closed interval method, because what you have to do, you still find these things called the critical numbers, which are where the derivative is 0 and undefined. But instead of taking the x's where this happens and plugging it into the original function and comparing, what you do is you plot all those answers on a number line, whatever those x's are, and then you pick test points. And you plug those test points into the derivative and determine if you get a positive or a negative. So if you get like a positive, then a negative, then a positive, then a negative, then you know your function goes up and then down, so you know that you have a max here, local max. And then here you'd have a local min. And then here you'd have a local max. So if this is called the closed interval method here on the left, you could say this is kind of like the open interval method on the right. And so going into what we're about to do, you have to be familiar with these two methods, right? Because we're going to use both of them. So on the test, one of the problems, the last problem, number 13, asked you to find like what A gives you maximum curvature. And A had to be bigger than 0. You had to use this method to figure that out. And then what was the other one? The other one had something to do with an interval 0, 2. I don't remember. Oh, well, oh, the maximum, you were trying to find the maximum, maximum speed. That's right. You were trying to find the maximum speed of a particle on an interval or something like that. And for that, you could have used the closed interval method. All right, that's it. I'm going to move on. Okay, so with all of that kind of in our toolbox and ready to move forward, now we start talking about maximum minimum values of a surface. So here, here's an example of a surface. I put some nice little ripples in it. So you can see that when we have a surface, it is possible to talk about little, maximum points. Like here looks like a max, that looks like a little local max, and then this, I'll do it in different color. The blue point here looks like that's like the highest point out of all of them, right? So the blue would be like a global maximum, and then the pinkish ones would be like local maximums. So this point right here might be like, you're the king of the hill, right? But only that hill, right? The king of all hills is this one. So that's kind of the idea here. Local, global, same ideas, same concepts, just three-dimensionally. And then you could say the same thing for minimums, right? On the bottom, you might have some local minimums and local maximums. I mean, sorry, local minimums and maybe a global minimum. Okay, so this is just to illustrate we have the same concepts in play here. Oops, I need to scroll down, sorry. So this is just some language. This picture right here. This is it out of the book. Looks a little different. You have this idea of an absolute maximum, local minimum, absolute minimum. And so this just goes through and gives you some language. But the big thing here is this right here, the second derivative test. We had this also in Cal 1, but this is the thing we're going to need. Okay, this gives us a method for finding the local maximums and local minimums. All right. So it says, suppose the second partial derivatives of some function f are continuous. So when we're talking about f here, we are talking about a function f of x, y, right? So z is some surface that is a function of x and y. So it passes the like vertical line test, so to speak. We draw vertical lines, punch through our surface. We're only going to punch through in one point. So if we have that, and we suppose that the second partial derivatives of the function are continuous, meaning if we take the second partials, we get nice functions that are still defined. So if we've got the second partials are continuous on some disk with center AB, suppose that the partial of f with respect to x at some point is 0, and the partial of f with respect to y is also 0 at that same point. That is, that point AB is a critical point of the function. Then we will define this thing called capital D, and this is what it'll be. It's going to be this computation we do right here. Okay, so let me just kind of back up and tell you what we're going to do. We're trying to find local, like where these little hills and valleys occur on a function. And to do it, what we're going to do is we're going to say, first, where is this true? At what points are the partial with respect to x equal to 0? And then where's the partial with respect to y equal to 0? And that means where are the slopes of the tangent lines in those two directions? 0, flat, right? That might be where we have a local max or a local min. To actually figure out if it's a local max or min, we have to calculate this thing called D, which turns out to be a number. Okay, we're going to have to do this calculation right here. And once we calculate that D will tell us whether or not we're looking at a local max, a local min, or neither, which we will call a saddle point. So if we calculate D, and it turns out to be a positive number, then it could be A or B here. It could be a minimum or a max if the D is positive. So the next thing you have to do is look at the second partial of f with respect to x. You have to do partial with respect to x twice. Look at that and figure out if it's positive or negative. If it's positive, then you have a local minimum. And if it's negative, you have a local maximum. And then if you calculate D and get a negative number, well, then in that case, you don't have a local maximum, and that's referred to as a saddle point. Okay, so let me try and explain. I'm going to try and explain this with I guess, let me see here. Let me do it like in the back from the Cal 1 perspective. Let's say I have a function. This is back in Cal 1. And let's say at this point, I tell you that the derivative, the first derivative is 0. Okay, let's say at this point A. I tell you that the first derivative is 0 there. Is that enough for you to decide that that's a local max or min? Just that we have a flat tangent line. It's not, right? Because you could have a curve that does, I don't know, it could do this. That's supposed to flatten out. It could do that, which in that case, it wouldn't be a max or a min, right? So what we then look at in Cal 1 is the second derivative. So what if I tell you at that point, the second derivative at A is positive? What would that tell you that the function has to look like? What does the second derivative tell you about the shape of the graph?
The concavity.
Concavity, right? And a positive concavity means it's concave what? Up or down?
It's concave down.
So positive, right? I always think of it this way. If it's a positive number, positive people smile, right? Positive people are always happy. A smile looks like a concave up. So if your second derivative is that, then you're concave up. And now, is that enough for you now to tell me whether or not this is a local max or min? If you have to be flat here and you have to be concave up, then don't you agree that you would have to, your curve would have to do this? And that would mean it's a local minimum, right? But if your second derivative was negative instead, then you'd be concave down there, and then you'd be looking at a local max. So this is the same exact sort of thing we're doing here. We have to investigate something to do with the second derivatives, second partials, which has to do with like a concavity. And we're doing it to try and figure out where we have these hilltops and valleys. All right, is that enough for me to just move on and let's do an example? You ready for that? Where'd it go? There it is. Okay. All right, so these local maxes and mins are called extreme values. So what we want to do now is we want to see if we can find the extreme values of this function. And I drew the picture for you. All right, and we're going to see if we can find the extreme values or not. So questions before I start? Okay, the first thing I want to do is I want to figure out where is the first partial of f with respect to x equal to 0. After that, I need to find out where is the partial of f with respect to y equal to 0. So that's like kind of like in Cal 1 where we're saying, hey, where's the derivative 0? And that gives us where we have a flat tangent line. So we need some partials. So let me take some partials. The partial of f with respect to x is negative 2x. And the partial of f with respect to y is 2y. Now I just set them both equal to 0. I'll do them one at a time. This has a solution of x is 0. And then this one over here, 2y equals 0. The solution here is y is 0. So what we're trying to find is we're trying to find some point A and B, A, B, right? Some point in the domain of this function. So remember the ground is like the domain. We're trying to find some point on the ground that when you look at that point, it creates flat tangent lines for the partial derivatives. And what it looks like is that our x coordinate must be 0 for this to happen, and our y coordinate must be 0 for this to happen. So what we have is one critical point. And this is the only one. It is the point 0, 0. Is everybody clear? Once we have the critical point, we now need to calculate capital D. Now capital D, let me go grab our formula. I'm just going to grab this whole thing. I'll throw it right here. So far what we have done, okay, if you're following this second derivative test, we have found this critical number where the partial with respect to y was 0 and the partial with respect to x was 0. That's this piece. That's what we've done. And now what we need to do is calculate D. But look at what D requires. It requires second partials, which means I have to go figure out what all the second partials are. So I'm going to do that on the side. What's the partial of f with respect to x twice? So that means just take this answer, right? What's that? What's the derivative of this with respect to x again?
Negative 2.
Negative 2, okay. What's the partial of f with respect to y twice?
2.
2, okay. And then look what else we need. We needed xx, yy, and we need xy. So what's the partial with respect to x followed by y?
0.
0, because we're just taking derivative of this with respect to y, but that means there's no y's in there, so that's just 0. So now what we do is we just plug it all into here. Okay, so let me do my D here. I think what I'll do is I'll copy this D so I can write underneath here and slap it right here. Okay, so we said D is equal to D at this critical point at 0, 0 should be equal to the second partial of with respect to X. So X twice at the point 0, 0. But look, the second partial is a constant, isn't it? It's just -2. So that's just -2. And then we have partial with respect to Y twice at 0, 0. But again, it's just a constant. And then minus whatever the partial with respect to X then Y at 0, 0, but it's a constant, right? Whatever that is squared. And this turns out to be -4 minus 0. This is just -4. So capital D, the capital D that we're getting here is a negative number, right? And according to this, if we get a negative number for D, then that point is not a max or a min, which means it is a saddle point. And that means that we have no extreme values. Okay, we don't have any. There are no little hilltops or valleys here. And I hope that when you saw the there it is. When you saw this picture, here's the graph. I hope that you would agree with me that this surface has no local max or min. Because you have to remember, this sheet continues going down, and then it goes, up over here, and then it goes down. So there should be no little hilltops or valleys there. The point that we were looking at was the point right here in the origin right there, that point, and that was our saddle point. In one direction, you could say it kind of goes down. In the other direction, it kind of goes up. So there's your saddle. Any questions on that? Good.
I'm a little confused on what capital D tells us.
What it tells you?
Yeah, so if capital D was equal to -4, what type of information can we pull from that?
Only if it, okay, so all capital D tells you is, well, if capital D is negative, you can't have a max or min. You have to be a saddle.
Okay,
If it's positive, then you're either going to have a max or a min. But then you have to continue with the what it says here. So let's say just for the sake of saying it, let's say that number would have been +4. Okay.
Mhm.
Then we would have been either here or here. So then what we would have to look at is the second partial with respect to X, which up here would have been what?
-2.
And since it's -2, it would have been negative, right? And then that tells you that you're at a maximum. You have a local maximum there.
We don't have a condition for if D equals 0.
That's right, we don't. I'm glad you brought that up. So what do you think happens if D is 0? Just what does your instinct tell you? If D is 0, then what's going on?
The point is not in the domain, probably.
Maybe
Or something.
Just not a critical point.
You could still have a critical point. It means just that the test fails. That's all it means. It means that you cannot conclude what's happening there. That means that it might still be a max, it might still be a min. It might be a saddle point. It's the worst case scenario, okay, is if D is 0, because then this test will fail. So it's like a defective pregnancy test, right? It's doesn't mean you're pregnant, doesn't mean you're not pregnant. It just means that you need to go buy a new test, right? So we would have to do something different in order to figure out whether or not you're looking at a local max or min. Now, within the scope of this class, that's not going to happen. But I know on one of the mini exams, I do give you a problem where that does happen. But you can still solve the problem because you can look at it from the Cal 1 perspective. So, yeah, good question. Let's look at the next one, the next example. Okay, so I'm going to copy this. And I'm going to give you a moment to take this and look, if we're going to be trying to find the local max min values, would you agree that to calculate D, we're going to need the partial with respect to X, we're going to need the partial with respect to X twice, we're going to need the partial with respect to Y, the partial with respect to Y twice, and we're also going to need the partial with respect to X then Y. Like all of those are necessary for us to do this. So take a few minutes. I'm going to go refill my drink. Take a few minutes. I'm going to come back and I'll just call on some people to give me all these things, okay? Y'all can keep working, but I'm going to call on some people here. So how about Ezwa? Are you here?
Yeah, I'm here.
Okay. How about the partial of F with respect to X?
That would be 4x cubed minus 4y.
Yep. Good. And then you want to go with the respect to X again?
Yeah, it'd be 12x squared minus, I'm sorry, just 12x squared.
Okay, good. All right. Do you want to keep going?
Yeah,
Okay. So how about with respect to Y?
it'd be 4y cubed minus 4x.
Okay. And then with respect to Y again?
It'd be 12y squared.
Okay. And then how about with respect to X followed by Y?
Then that'd be just -4.
Perfect. Good. Everyone okay with that? All right. Good, 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 good. Now, what we need to do now, okay, is we need to figure out first where these two conditions are held. So where is the partial with respect to X equal to 0, and where is the partial with respect to Y equal to 0? In the previous problem, that the algebra on that was pretty easy, right? Because we did the partial with respect to X, which was this. We set it to 0, we got 0. We set that equal to 0, we got 0. Everything was great. Here, it's a little different because we've got to set the partial with respect to X equal to 0, which means we have to set 4x cubed minus 4y equal to 0. And then the other equation we have to figure out is where's the partial with respect to y equal to 0, and that's 4y cubed minus 4x must equal 0. And immediately you should see we have a problem, because if I'm trying to solve an equation and I have one equation and I have two variables, then you cannot solve that for X without knowing what Y is, and you can't solve for Y unless you know what X is, right? So you'll never be able to give me a unique solution here, and you'll never be able to give me a unique solution here because same thing. Do y'all understand that? So it looks like maybe we're stuck, but if they both have to be equal to 0, right? Then we can set them both equal to one another, right? If this has to be 0 and that has to be 0, then how about we just say, well, where are they equal? See, the thing is, we're trying to find this X and this Y that make both of these true, but they have to be true simultaneously. Like if you give me an X and a Y that makes this true, but not this one, then you can't use it. The critical point has to satisfy both at the same time. So I'm setting them equal to one another. And now, oops, I forgot a 4X here. And how about I'm going to divide everything by 4, just because I'll get rid of a 4 there, and that'll be nice. And now I try and solve this. Any ideas? We still have one equation, don't we? With 2 variables in it. So did this get us anywhere then? Let's keep working. How about this? I'm going to bring everything over to one side. Yeah. Okay. Anybody recognize the first 2 terms there as being a difference of cubes? Could you factor that? Could you? It would be X minus Y times X squared plus XY plus Y squared. There I'm using the difference of cubes formula to factor this. And then I have here plus X minus Y. Now, the reason I did that is because now if I kind of squint my eyes, I have X minus Y here and X minus Y here out. When I do that, it would be, let's see, if I take X minus Y away from that factor, I'm left with that factor. And if I take X minus Y out from here, I'll have plus 1 equals 0. You all right with that? See, now I have factored, right? I factored this. So if I factor this, I can set each factor equal to 0. So I can set this to 0 and I can set that whole thing to 0. So the first one, X minus Y equals 0, is one equation I have. And then the other one is that X squared plus XY plus Y squared plus 1 must be 0. The first equation says X must be Y. Let's go with that first. If X has to be Y, then I can take this equation and let's just replace Y with X. And now I can solve for X. So this will give me factor out an X squared, sorry, let me factor out a 4X. I get X squared minus 1 equals 0. Y'all buying this? And I can factor X squared minus 1 to be X plus 1, X minus 1. And so how many solutions do I have here? Got 3. Good. So I've got X is 0. I've got X is negative 1. I've got X is 1. And because we said that X had to be Y, right? We're just following this logic here, that if X has to be Y, then I can tell you that Y here would also have to be 0. For this one, Y would have to be negative 1. And for this one, Y would have to be positive 1. So we have 3 critical numbers. They are 0, 0. Critical points, I should say. I'm sorry. Negative 1, negative 1. And then 1, 1. Got 3 different critical points at this juncture. All right. Any questions on that so far? Now, how about the other equation? What about the other equation? That looks like that might be a little bit tough, huh, to solve. It might be a little tough to solve. So, you know, when we were up here and we said, okay, let's set these two equal to one another because they both have to be equal to 0. And we said that then you could bring this over and you could factor, right? The way I did, factor this. I should let you know ahead of time here that there's no like universal way to solve equations. Like you have to go figure out how to solve the equations, right? It's up to you at this point, the algebra. Maybe there was another way we could have done that. Because this equation, I think, is going to be difficult for us to do. Would you all agree with that? It's going to be hard? Okay. So maybe we do have 3 critical numbers, but we're not completely sure that this is all of them. So I think what I'm going to do is go back up to, let's go up to this equation because that was like the cleanest one we had. And let me just kind of revisit it, see if there was anything else we could do algebraically. And if it seems to you right now that I'm kind of like wavering, going kind of like, you know, let's try this, let's try that, it's because that's what you're going to be doing. Okay, you need to get used to the idea of there's not going to be one clear path here. You've got to be willing to try different things. So is there anything else I could have done? How about this? Could I have done x cubed plus x and then minus y cubed minus y, like that? Could I have done that? Equals 0. So I brought everything over, okay, but instead of doing it this way, I put the x's next to one another and then the y's next to one another, right? Does this help? Let's see. I can factor out of the first two. I can factor an x out. I'd be left with x squared plus 1, right? And then on the other one, I could factor out a negative y, and then I'd be left with y squared plus 1 equals 0. And this right here, we're pretty much stuck, right? Do y'all see that we can't really do much with this? Like they don't have a common factor that I can pull out. Where over here, I noticed the difference of cubes and that allowed me to do something and then see a common factor and it got us somewhere. Are y'all with me? With me? Okay. So I just want to show you that there are different paths that you may go down and get to an algebraic expression that you're going to be kind of stuck on. Like, just be prepared for that. Does anyone see anything else that we might have been able to do? Any other algebra that maybe you'd want to try? No? Okay, we can't factor this, right? We can't factor this. Could we try and solve it for x or y? We could try. Let's try and solve this. Let's just try and solve this for, let's say, let's try and solve it for y. I don't think we're going to get anywhere, but I'm going to get all my y's on one side. Let's see, negative x squared minus 1. And if I try and pull a y here, what's going to happen? I'm going to get x plus y equals negative x squared minus 1. So again, we're stuck because you can divide through here, but then the right side's going to have y in it, and the left side will also have y. So you can't get y isolated. This is basically an implicit equation. So is there any hope for us to know whether or not this is going to give us a solution? Do you have any ideas on how we might be able to go about that at all? Okay, let me ask you this. Is this number always going to be bigger than or equal to 0? Yes?
Yes.
Yeah.
Okay, is this number always going to be bigger than or equal to 0?
Yes.
Yeah. And I add this number, which is always bigger than or equal to 0. So these three numbers together are always positive, right? If we put those together, those have to be greater than 0. So that can't be true, but we have an x times y, right? If they're both, what if they're both, what if both x and y are both positive numbers? What can you tell me? This would be positive, wouldn't it? And so you'd have 4 positive things you put together, and then it would never be 0, would it? Right? Okay, so if x and y are both positive, then there's no solution to that equation. What if x and y are both negative numbers? Well, if these are both negative and I multiply them, I'm gonna get a positive, right? So I'd have a positive here, positive there, positive there, positive there. Add them all up, can't be 0. So there'd be no solution here. No solution here. So the only way we're going to actually possibly have a solution is if x is positive and y is negative, or if x is negative and y is positive, right? Those would be the only scenarios where we would have an issue. Because then it would be possible if, let's say x is positive and y is negative, that would be a negative number. And it is possible that I take a positive, add a negative, and get 0, right? That is potentially an issue. So maybe there's somewhere else we can determine that can't happen. Might help if we, so
for the first, on the first equation, when you put them equal to each other, what if you just put the x's and y's onto one side, then onto the other side? Would that make a difference? Because the cube would, if it's negative, it would give you negative, but then it would add itself back. If that makes sense.
You want me to put the x's on one side, y's on the other? Is that what you said?
Yeah, and then do the same thing where
If you
you're
did all the x's on one side, you would get that, right? Is that what you're saying?
yes.
Okay, and then what?
So like, wouldn't you be able to go through the same process as what you're doing right now? Because if you cube a negative, if you cube a negative, it'll still be a negative, but when you add another one to it, it'll become a positive.
When you add it, it'll still be negative.
It'll still be, okay, yeah.
You have it, okay, Adam, you're on it. You're on this right now. You are on the cusp of having this. Does everyone see where, can anyone help Adam get there? He's almost there. Remember, this is the case that we have to look at, right? Right here. We're concerned that this equation might have solutions, right? That's what we're concerned about. This might have solutions. It's impossible for us to find it because we don't have any algebra to do it, okay? We know that if both the x and y are positive, then this is fine. There's no solution here. If both of them are negative, there's no solution here. Are y'all okay with that? But if one of them is positive, the other one's negative, then it looks like there could be a solution here. But Adam is saying that if we have to satisfy this equation, then this must hold. And then Adam was saying, let's go with this one. Let's go with x is positive, y is negative. Okay? If x is positive, what can you tell me about this side of this equation?
It's going to be positive.
It has to be positive. Okay? But if y is negative, what can you tell me about this side?
It's going to be negative.
It's got to be negative, right? Do you all see that? Any number cubed, any negative number cubed is still negative. And if you add a negative number, it's the same as subtracting. So this would be minus or negative, wouldn't it? And there's no way a positive number can equal a negative number unless we're talking about 0, right? If x and y are both 0, then that equation is true, right? But don't we have that here already? Don't we have 0, 0? Haven't we considered that? So this right here is enough to say that there's no solutions here. But you have to go through the logic of it. You can't just say there's no solution. You have to somehow express that you've thought through the scenarios. That's not nice, is it? That's kind of nasty. Are there questions? I mean, welcome to Max Min on, Cal 3. It's not as simple as the Cal 1 stuff. There's a lot more you have to consider. All right, so I'm going to proceed now. We have our critical numbers. We have these 3 critical numbers from this, and then we know there's no critical numbers from this. Now we have to get capital D. So let me see here. I'll paste this sucker in here, see if I can't fit that. I'll put it right there. All right, so we need some second partials. They were up here. I'm gonna grab these and bring them down. All right, so here we go. All right, so let's talk about what's happening at the point 0, 0 first. At 0, 0, let's figure out what D is, okay? D at 0, 0 means we're gonna do this formula. We're gonna take the partial with respect to X twice and then plug in 0, 0. So I'm gonna take the partial with respect to X twice, plug in 0, 0 into it, then times the partial with respect to Y twice, plug 0, 0 into it, and then subtract from that the partial with respect to X, then Y at the point 0, 0, and then take that and square it. And I'm gonna try and figure out this positive or negative. So who wants to tell me what this first one is? What's this?
0.
0, right? Because you're taking this right here and you're replacing the X with 0 because we're looking at the point 0, 0. So this should just be 0, okay? Times, and now partial with respect to Y twice at 0, 0 means this
Also
one,
0.
plug in 0, you also get 0, good. And then minus, how about this one? Well, that's -4 no matter what, right? So -4 squared. So you square the -4, you get 16, but then you make it negative, so you're going to get -16. Well, that's less than 0. And what happens when you have D less than 0?
There's no, oh, it's a saddle point.
Saddle, right? So we have a saddle at 0, 0. Now we have to do the same thing at the point, let's go with -1, -1. Okay, so I need to calculate D at the point 1, -1, -1, which means the partial with respect to X twice at -1, -1, times the partial with respect to Y twice at -1, -1, minus the partial with respect to X then Y at the point -1, -1, all of that squared. All right, so what happens here? Partial with respect to X twice, that's this one. And we're replacing X with -1.
It's
So what do
12.
we got?
12.
Just what?
12.
12, okay. And then times this one,
Mhm.
also 12, right?
Yes. Mhm.
And then minus, well, we already know that this is -4 and squared, so this is -16. And that's 144 minus 16. That's a positive number, right? For sure a positive. So now we're talking about it's either case A or case B. So now we need to investigate the second partial with respect to X. So that right there, which in our calculation, isn't it this one right here? It's that one. Is that positive or negative?
Positive.
It's positive, right?
Mhm.
And so we're looking at this case right here, case A. So we have a local minimum at -1, -1. And now we have to check the third one. So D of 1, 1. I'm gonna do this one a little faster. So I do this one first. I plug in 1 for X, I get 12 again. Then I plug in this one, I plug in 1 for y, so I get 12 again, and then minus, same thing for the other part, 16. This is a positive number. It's actually identical to the other one, isn't it? And so you're going to have, again, a local minimum. So when we graph this function, we should have a local minimum at -1, -1, local minimum at negative at 1, 1, and at 0, 0, we should have a saddle point. Okay, that's what this thing looks like. Are you ready to see it? Two local minimums, and then a saddle in the center here. Okay. Of course, this thing keeps going up, right? Like this keeps on going. So it's almost like a parabola, right? Almost. So quite a bit of work going on here, right? Quite a bit of work. The algebra starts to get messy.
I have a question.
Yes.
On the problem we just finished right now, you see where you put x equals 0 right there, x equals 0, on the left, x equals -1. So we're supposed to just assume because x equals 0 and -1 and 1, that also y equals 0, -1 and 1.
No, it's because of this relationship we established right here. When we had set this factor equal to 0, I moved the y to the other side and said, okay, so whatever x is, y has to be the same thing. So when we solve this equation for x, whatever we got for x, that was also y. Whatever we got for x, y has to be the same. Okay? If this had been like x equals 2y, then we would have to double these answers.
Okay.
You with me on that or no?
Yeah, because I guess I'm assuming that since you factored on the top there with the green and red, where x -1 in parentheses times the other one in parentheses equals 0, you just found that to be the solution for x minus y equals 0, which just means x equals y.
Yeah, and once I knew that x equals y, I went back up to this first equation and I replaced that y with x. See, because if x has to be y, or if you want to say it the other way, if y has to be x for this to be true, then I can replace that y with x. And that's why I came down here and wrote this equation. And by doing that, I now have a single equation with a single variable. And then I can solve for that.
Oh, okay, I understand.
Let's do another one. All right, so I took a lot of time on that last one, so I'm going to go a little faster through this one. So let me get all these partials first. Partial with respect to x, let me see here. 3x squared y. And then plus 48, 24x. Okay, let me go and take the partial with respect to x again. So 6xy plus 24. And let me get the partial with respect to y, which is x cubed minus 8. Partial with respect to y again should just be 0. Okay, that's interesting. And then the partial with respect to x followed by y, that would be 3x squared. And that's it. So I think it's clear that if you're having trouble finding partials, then these problems are going to be difficult, right? Because you're going to, if you mess that up, everything else after that is done, right? So you got to make sure you're comfortable with this. So are there any questions on these partials? All right, here we go. Let's try and figure out where is this true and where is this true simultaneously, right? So I need to know when 3x squared y plus 24x, I need to know when that equals 0. And then the other one, I need to know when x cubed minus 8 equals 0. Oh, that's nice, right? That second equation is nice. There's only one solution to that one. right? There's only one number that you cube to get 8, and that's 2. Once I know that x is 2, then I can go to the other equation. I can say, okay, well, x has to be 2, right? So that means that this turns into 12y plus 48 equals 0. So I'm using this information that x has to be 2 from this to take that back and plug it into this one. And now I have an equation with y, so y has to be what, -4? So in order to satisfy the two conditions, we have only one critical point. So the algebra here was a lot better than the last problem, for sure. And now we calculate D, right? So I think I'll take some time here to just write down what D is. D at the point 2, -4 should be the partial with respect to x twice at 2, -4 times the partial with respect to y twice at 2, -4 minus partial with respect to x then y at 2, -4, that quantity squared. And now we just plug in, let's do XX. So I have to replace, let me take this a little slow here. I'm gonna go 6 and then times the X times the Y and then plus 24. That's this right here. And then the partial with respect to Y twice, is 0, right? This is gonna kill all that out. Minus, okay, and then the partial with respect to x then y, which is 3x squared. I replace the x with 2, so this would be 3 times 2 squared, right? And then all of that squared. So what are we getting here?
Oh, we're gonna always get a negative here.
We're going to get a negative number here. This is going to be less than 0, and that means we should have a saddle. But it also means there's no local maxes or mins. There's no hilltops, there's no valleys. Sorry, that's a saddle point. Let's take a look at it. Really kind of an interesting looking surface. And we found the only point on this surface that is a saddle point is that point right there, the point 2, -4. And then I put here 2, -4, 48. You get 48 when you actually plug in 2, -4 into the original function. So if you plug 2 and -4 into the original function, it would spit out 48. So you go up 48 units high. And there you are, you're on this little ridge. All right, I'll give you a few minutes. You go ahead and see if you can't work out these partials. while I'm waiting on people to kind of work these out, does anyone have any questions on it? Anyone have any issues that you want me to clarify?
It's just gonna get really ugly.
Okay, I think we should talk about the first derivative here, because this is getting ugly. When you take the partial with respect to x, you have e raised to something, right? So anytime you take derivative of e raised to anything, it's itself, right? But then you have chain rule, which says now you take derivative of what's in the exponent, but we're doing it with respect to x. So luckily for us, the only thing you have to worry about is this negative x squared, so we get negative 2x. And then I just slid the negative 2x out front. There we go. Because we have to take derivative again. And because we have to take derivative again, I have to treat this like a product rule. Right down in the middle here, we have a product because there are x's here and there's x's up in here. So when I do the product rule, I do derivative of this one, which is negative 2, times this one, which is that, plus now I take derivative of this e thing again, which I already did in the previous step, right? So I'm going to get itself and then times the negative 2x. But then to finish off the product rule, I have to hit it with the negative 2x again. Messy. And then on the next step, what I did is, since these both had the e raised to that stuff up there, I factored it out. And that left me with a negative 2 from here, and it left me with these two multiplied, which is the 4x squared. So that's my partial of f with respect to x twice. Now, the one with respect to y twice, I think is going to be worse. Because first it's itself. Make this a little bigger. And then we have times the derivative of what's up here with respect to y, which will be 4 minus 2y. Is that all right? And I can leave it like that and do a product rule this way, but I don't know why. I always like to put the easier stuff up front, so I'm going to do it like that. Okay, so now with respect to y twice, so I have to do product rule right there. So derivative of the first part with respect to y is negative 2. And then e, I'm just going to say e to that box because that's going to be the same here. And then I say plus, now derivative of e to all this with respect to y is going to be e to all that stuff. And then I'm going to have the 4 minus 2y from the chain rule. But then to finish off the product rule, I have another 4 minus 2y. Now I can factor out the e raised to that stuff, and I'll be left with negative 2. And then I could actually multiply these two together, couldn't I? And get like 16, what is that, minus, we're going to have like minus 16y and then plus 4y squared. Are y'all following what I'm doing? I'm seeing some heads shaking, yes. Okay, last one. Let's do the partial with respect to x followed by y. So I've got to go up to this one right here. I'm going to do the partial of this with respect to y. The good news is negative 2x then is a constant. So it's just going to be negative 2x e raised to all that stuff times now the derivative of what's up here with respect to y, which would give us the 4 minus 2y again. So no product rule there because negative 2x is not a variable. All right, does that look fun or what? So first thing, we need to figure out where the partial with respect to x is equal to 0. So I'm going to go back up here to this. I'm going to set it equal to 0. I'm using the box because I don't feel like writing that out every time. Is that all right with you? And why does it not matter here? Can somebody tell me why I can get a solution this easily without even having to consider what's happening here?
Well, anything raised, the e can never actually be 0, so it's going to matter what it's in front of it.
That's right. So e raised to anything can never be 0. So when I'm looking at this, I can just get rid of that because it's multiplication here, and I can just set the negative 2x equal to 0. And that gives me a nice solution, 0. And then when I do the other one, partial with respect to y equal to 0, that's this one right here. That's 4 minus 2y times e to all that junk must equal 0. And same argument, this cannot be 0. So all you have to do is set the 4 minus 2y to 0. And that means y must be 2. And so we only have one critical point. Our only critical point is the point 0, 2. Okay. Now we get D. D at the point 0, 2 should be the second partial with respect to x twice at 0, 2 times the partial with respect to y twice at 0, 2 minus the partial with respect to x followed by y at 0, 2, whatever that quantity is squared. All right, let me ask somebody, because I feel like I know Benjamin, people with their cameras on I know are participating, but let me see here. There's a lot of people not here today. I'm wondering if that midterm kind of scared people away. How about Fabiola? You there?
Yes, I'm here.
Okay. Are you dizzy? Are you dizzy yet?
No, I'm just trying to catch up while you're going.
Okay. So this fxx at 0, 2, I just want you to evaluate this expression
right
at x is 0 and y is 2. What would we get?
1.
So e to the,
all of that would 1.
so that'd be 1, right?
And then 1 times negative 2 plus 4x squared, negative 2.
Negative 2. Everyone all right with that? That turned out to be e to the 0, right, Fabiola?
Mhm.
It was e
Yes.
to the 0.
Oh,
Okay,
right,
so
yeah.
that piece right there is that. So that's a negative number. All right, good. Let's go on. Who's up? Benjamin, I know you've already participated, but I'll call on you anyway. Uh-oh. I lost my my pen stopped working. So give me a second. I've got to undo something here. But Benjamin, you can go ahead and figure out what the next piece is. Shit. See if that brings it back to life or not.
Quick question, really quick. Sorry to interrupt. You said that E is negative. Why is E negative again? Where does it end up?
Why is E negative?
I was just looking at, like you said, that it's -2 at the end. Oh, never mind. Never mind. I see. I'm so sorry. I'm so sorry.
Yeah, you got -2 from here, right?
Yes.
Yeah, okay. All right, Benjamin, did you get the other part? This one?
Yeah, just 1 second.
Okay,
Sorry.
yeah. We should still get e to the 0, shouldn't we?
Yeah.
Yeah, so that should just be 1. And then I'll let you get that other part here. X
be
is 0,
negative.
y is 2.
Should be
Go ahead.
-2.
You got -2 again?
Yep.
I'll trust you. And then equals, let's see, or minus, and then here at 0, 2. Now we got to plug in 0, 2 into this. And what will that be?
0.
Anyone? 0,
Zero.
right? Because this X is 0, so it should just 0 that out. All right, so we've got -2 times -2. That's going to be +4, right? Minus 0. So this should just be equal to 4, which is bigger than 0. All right, so that means we either have a max or a min. Okay. Now to determine if it's max or min, all we look at is, Caden, what do we look at?
The second partial with respect to x,
Which is, in this case,
-2.
-2. All right, so what does that tell us if it's negative?
It's a local max.
Local max. The way that I remember that is that this is kind of like, this is like the concavity check. If it's a negative number, you're like a frown. So you're like at a max. And if this part is positive, then you're like smiling. So you're at a min. That's the way I remember it. The D just tells you either have a max or a min. So if the D is positive, you either have max or min. And then this one is the smile or frown. Okay, so good.
Real quick, I don't
Yep.
know if you went through it, but the 4y minus x squared minus y squared, that's 0 for on top of the e.
Yeah, it should be. If we plug 0 into, I can pick any of these. Let's just pick that one. If we plug in 0 for x and 2 for y, we get 4 times 2 minus 0 squared minus 2 squared. And so we get, wait a minute.
Yeah. That's why I was wondering. I thought it was e to the 4.
Is it e to the 4?
Yeah.
Oh, shit.
Yeah, I didn't want
It
to.
is e to the 4, isn't it? Do y'all agree it's e to the 4? I think when Fabiola was doing,
it's not going to change the answer anyways.
it's not going to change the answer. That's okay, but it is e to the 4 because this right here would be e to the 4. This would be e to the 4. So you would still get a negative number here, and you still get a negative number here. These two multiplied would still be positive. This is 0. So we kind of get lucky here. Who said that? Who pointed that out?
It was me.
Okay,
Adam.
thanks, Adam. Yeah, that was just, I just overlooked it when Fabiola was doing that. I think I forced her to say 1. Okay, but that should be just 4, right? This is 8, take away 4. Somewhere I was looking at a 2, but okay. So we have a local max still at 0, 2. Let's look at the picture. Here it is. It's like a pimple function, right? It's just like, oh, you got a pimple. There it is. All right, so we could keep going like on and on. Here's another example. I'm not going to work this one, but as you might imagine, the algebra of this one would be a little different. You know, here it is. You got to do all your partial stuff for it. And for this particular problem, you actually have four local minimums. So you get 4 critical points here. Here's another one. Here you wind up getting, 4 saddles and 1 local max. And due to time constraints, I can't go through all of these. Okay, here's a bonus one. Okay, for those of you who want to do a bonus problem, here you go. Find the local max and min values of that. Let's just say I'll give you a week to turn that in. Just send it to me through Canvas as an email attachment if you're interested. You're gonna probably run into some issues, but I will let this problem replace one of your problems on your midterm.
Sorry, you said due in a week?
Yeah, in a week. All right, we good? Now, the other two, I encourage you to do those. And on this one, a little hint, just multiply it all out first. So that when you take partials, you don't have to do a product rule. Like just expand that all out first and then do your partials. Here, this one's a nasty one because here you have to you bring these up as x and x to the -2, y to the -2, and then you go do your derivative and stuff. So it can be a little bit messy. Yeah, extra credit. Yes, Daniel, do you have a question? Did you miss that?
No,
Yeah.
I was just trying to make sure that it was, I wasn't sure if it was exactly extra credit. Then you said it replaces a question and I was like, okay, got it.
Yeah. Okay. All right. So what we've done up to this point is we've said, hey, if somebody gives us a surface, right? Can we find local maxes and local mins? So that's like when I started this whole thing and I said, where is it? It wasn't on one of these. Remember I said in Cal 1, there's a closed interval method and an open interval method, right? What we've done would be kind of the same as the open interval method because we just have a surface and we're trying to find the local highest and lowest points. Now what we want to do is see if somebody gives us a surface on a restricted domain, can we find the absolute max and absolute min? Okay, can we find the highest and lowest points on a surface if that surface has a restricted domain? So to do that, we first have to get some things, some language and stuff out of the way. If we're trying to find the absolute max and min of a function on a closed bounded set, we have to understand what a closed bounded set is. So remember, the ground is our domain, right? The ground is a domain and the surface is somewhere above it or below it or something, but the domain is the XY plane. When we're talking about the XY plane in the domain, we have the concept of a closed set, which would be like these two, a circle, like a disk. That would be all the points within the circle and all the points on the boundary. That would be considered closed. A square or a rectangle, including the boundary, would be closed. Sets that are not closed would be things like this, where you have like a disk, but you're not including the boundary. That's not a closed set. Or if you have a disk, you include the boundary, but you're missing one point, that would not be closed. Or if you have like a rectangle and you're missing the boundary, that wouldn't be closed. So to be closed means in two-dimensional space means that it contains everything on the inside and all of its boundary points are all there. You have to have all the boundary. Now, a bounded set is one that is contained within some disk. In other words, it is finite in extent. So let me try and draw something here. So, oh, I can't draw on this one, I forgot. I'll draw it on another one. So in two-dimensional space, that would be closed because it contains all the points inside and all the boundary points. This would also be closed if that extended forever in both directions, like a strip, just like a strip in two-dimensional space that went forever. Okay, that would be unbounded. To be a closed bounded set, you have to be contained. You can't go in one direction forever. So what we're looking at right now are surfaces that are restricted to, their domain is restricted to a closed and bounded set. So this is the same thing in Cal 1 where we had a function on a closed interval. This interval started somewhere, stopped somewhere, and contained all the points inside. This is what we would consider to be a closed bounded set in one-dimensional space. It's just a line segment. In two-dimensional space, we have to have some sort of definition also, and that's why we're talking about this. All these points in this bounded set are going to be mapped into some surface, and then we're trying to find the absolute max and min of that surface above that set. Does it make sense kind of visually what we're trying to do? Are there any questions on that? This is much harder, okay? This is much harder to do than what we just did, which is why we do this after we do the whole capital D thing, because this is a lot more work. All right, so we have a theorem, okay? It says that if F is continuous on a closed bounded set D in two-dimensional space, then F must attain an absolute maximum value and an absolute minimum value at some points within the domain. Okay, so this is similar to a theorem in Cal 1 that said if you have a continuous function on a closed interval, you must have a highest and lowest point. Every continuous function has to achieve a highest and lowest. So this theorem just says, yes, we have the same thing here. So when we were in Cal 1, what did we do? I showed you this earlier. We figured out where the derivative was 0, where it was undefined. We figured out what those x's were, right? Whatever they were. And then what we did is we plugged those values into the original function, didn't we? Plugged them into the original function, then we compared them. And we also had to plug in the endpoints. So you just plug in your critical numbers into the function, plug the endpoints into the function, compare. That's going to be a problem for us. Because even if we find critical numbers, critical points inside the domain and plug them in, and figure out where these points might be happening, we also have to check all the boundary points too. And that's an infinite number of points. So I hope you see it's already problematic for us, as there's not a finite number of points to compare. But it's okay, we'll be able to deal with it. So how do you find the absolute maximum and minimum values of a continuous function on a closed bounded set? How do we do it? First thing we do is we find all the critical points. So that's exactly what we were doing in the previous problems. We figure out where the partial with respect to x is equal to 0, where the partial with respect to y is equal to 0. We're gonna do that same exact step, okay? But that's it, we're not gonna calculate capital D. We're just gonna figure out the critical points. Then we're gonna find the extreme values of the function on the boundary, and that's gonna be hard, okay? That's gonna be a hard part right here. And then we compare the largest of the values from steps 1 and 2 will give you the absolute maximum respectively. Now I have 15 minutes, so I do have enough time to do one of these. Let me, okay, yeah, this is a good visual here. All right, so let's read through this problem. Find the absolute maximum and minimum values of this surface on the closed triangle with these vertices. So here's the entire surface, okay? Here's everything. That's the whole surface. We don't want to look at the whole surface. We just want to look at that surface restricted to this domain, which is the triangle with those vertices. So let's see what that looks like. Here's the triangle. If we were looking from the top down, there's the triangle in two-dimensional space on the ground. Here's that triangle in three-dimensional space, all right? That's our domain. And what we're doing is we're saying, okay, only graph that surface. So here's the whole surface, right? We're only allowed to plug points into this surface that belong to that domain. So what you get, sorry, I hit the wrong thing. What you get is this piece. So I have to let me pull the original surface out of here. Do y'all see that green piece is the only part of that surface that corresponds to the points within that domain? Yes, you sure? We only want to look at that green patch, and we want to ask ourselves, on that green patch, where's the highest point? Sorry, where are the highest points, right? This is the highest point right there. It looks like it. That looks like our absolute max. And then one of these points here on the bottom looks like our absolute min. We've got to find those. All right, do you understand the task ahead of us, like what we're trying to do visually? We restrict our domain, we look at the surface just on that restriction, then we try and find the highest and lowest points. That's very different than what we were doing before, right? This was not, we had no restriction on our domain. We weren't looking for absolute maxes and mins, we're looking for local stuff, local. You know, we could tell you, yeah, that's a local max, but there was no way we could tell you that was the highest point on the whole graph. That was not something we could answer. Here, we're restricting the domain and now we're trying to find it. Okay. Just trying to contemplate whether or not I want to go after this right now. I have 10 minutes. I just don't know if that's enough time. How do you all feel?
I think it'd be best to just go through it.
You want to go? You want to see it? Okay. All right, let me copy the problem real quick and then let's talk about how we're going to do this. All right, so first thing I'm going to do is I'm going to find the critical points. So for critical points, what I need to know is where is the partial with respect to x equal to 0, partial with respect to y equal to 0. This is the same step in Cal 1 where what we're doing is we're trying to figure out where our derivative is 0 so that we can find potential locations of the absolute max and min. That's what we're doing, but we're doing it in three-dimensional space. So let me take these partials. Partial with respect to x, this is equal to y minus 1. And the partial with respect to y is going to be x minus 2. Those are nice equations to set equal to 0. So if I set that equal to 0, right, I should get y is 1. If I set that one equal to 0, I should get x is 2. So I only have one critical point. It's the point 2, 1. Any questions there? Okay, that critical point is a potential place where I have a max or min, where I have the absolute max or min. It could be, it could not be, but it's a place I need to look, all right? Now, the next thing I'm gonna do is I'm gonna look at the domain, okay? The domain that we're being restricted to is that triangle. So I'm gonna go ahead and draw it. So I go to the point 1, 0, and put a dot here. Go to the point 5, 0, 2, 3, 4, 5, 0. Put a dot here. Go to the point 1, 4, which is up 4, out 1, up 4, right here. And it's a triangle that looks like this. Now, this critical point we've had, is it in here? Is 2, 1 in this region? It is, right? It's 1, 2, it's up, it's right here, right? So that was our critical point. I just want to make sure that we're aware of the fact that that critical point that we found is in here. What if that critical point was not in here? What if this was like, I don't know, 7, 2? We wouldn't look at it, okay? Because we're only allowed to look in this triangle. All right. So we've completed the first step of finding a critical point. Now what we need to do is look at the value of the function along its boundary. This is where I said this is a problem because we have an infinite number of points to check. So the way we're going to break this down is we're going to break it down by looking at this triangle as 3 different paths. The first path is going to be the segment that goes from here to here. I'm going to call that line 1 because it is a line. I'm going to call it L1. Then the path that goes from this point to this point, I'm going to call that L2. And then I'm going to look at this L3. All right, let's talk about L1. On L1, here's what I can tell you. If we are moving along L1, if you're any point on L1, is there anything guaranteed you can tell me about the point?
It's 1 unit away from the line.
It's got to start 1 unit from here and go to 5, right? Can you tell me anything about the Y coordinate?
It's always 0.
It's always 0. So would you agree that on L1, every point that we have in there has some X coordinate, the Y coordinate is 0, and the X is bounded between 1 and 5? Would that be fair to say? If we're any point on L1, then it must have an X value between 1 and 5 and a Y value that must be 0. Y'all agree? Now, okay, well, what's the original function we're looking at? Here's the original function, right? F of xy equals 3 plus y at, xy minus x minus 2y. But if we are talking about a point on L1, then it's actually, the x can be anything between 1 and 5, but the y value has to be 0, right? So I can replace the y with 0 throughout the entire equation. And if I do that, I just get what? 3 take away x. Okay, so here's where you have to kind of open your mind up and think about what we just determined. What we are saying is this: if you are on L1, right? If you are talking about just being on L1, then this problem has reduced to you trying to find the maximum and minimum value of that function on that interval. So you've really reduced the problem down to this. I don't want to call it f, I'm going to call it something else. This right here, I could call it like g of x, right? Because it's only a function of 1 variable now. It's 3 minus x. And I'm trying to find the max of it on the interval 1, 5. Right? We want to find the max of this. Find the max of this on that closed interval. That's Cal 1, right? That's a Cal 1 problem. That's trying to find the maximum of a function on a closed interval. So you're now going to use the closed interval method for this, which is take the derivative of this, right? What's the derivative of that? -1. Set the derivative equal to 0. Figure out where the derivative is undefined. Well, is this derivative ever 0?
No.
No. Okay, so that's never going to happen. And is it ever undefined?
No.
Well, -1 is defined, isn't it? So that's never undefined, right? So what are the only places we're interested in then? If there's no critical numbers, go ahead.
1 and 5.
Only at the endpoints, right? That's the only interesting points we have to look at. So what I need to do now is say, okay, what's the value of that g function at 1? I'm talking about this point. And compare that to what is the value of that function at 5? So what is the value of g at 1? If I plug 1 in here, I get 2. And if I plug 5 in here, I get -2. Are you with me? Are you with me? So here, remember we had these critical points up here? We had the critical point up here, 2, 1. What we're saying here in this, if I could kind of illustrate what's happening here, is that we know we have these 2 points where something interesting is happening. The first point that we have is we know that anything on L1, the y coordinate is 0. And then we were just trying to figure out what x's were critical numbers. And since we didn't have anything from the derivative, we just looked at the endpoint. So we have 1 here and 5 here. And we know that when we plug that into the original function, it's going to spit out 2. And when we plug that in, it's going to spit out -2. That's what we know. Now what? What do you think?
You're gonna test the other two?
Yeah, I've got to go now to move to line 2. Okay, so line 2 is going to be more challenging. Okay, because on line 1, everyone could tell me that the the y coordinate had to be 0, right? That's what you could tell me. But on L2, the x coordinate's not 0 and the y coordinate's not 0, right? So how are we going to do that then? Let's put it on pause. How about on L3? Is L3 easier? What can you tell me about L3? If you're any point on L3, what can you say about it?
X equals 1.
The x has to be 1, right? Because we're right here at 1 vertically. So the x has to be 1. And then what about the y coordinate? But it can be anything, right? Anything between where and where?
0 and 4.
0 to this high, right? 0 to 4. So if you're on L1, every point on L1 has to look like the point 1y, where y has to be between 0 and 4. And now what we're going to do is we're going to plug that into the original function. What happens when we plug 1 in for x and y for y? So plug that into this original function. I have it written down right here in case you forgot it or we can't see it up there. So replace x with 1 and leave y alone. So you should get 3 plus x is 1, so y, and then minus x is 1, and then minus 2y. I'm going to get 2 minus y, I believe. And so again, we have now reduced this down to a Cal 1 problem. We have some function, I'm going to call it g again. We have some function g of y, which is equal to 2 minus y, and we're trying to find the max and min of that on a closed interval 0, 4. So you do the same thing we did over here. You take the derivative, you set it equal to 0, figure out where it's undefined, and you're going to have the same result as over here, right? It's never going to be 0, never going to be undefined. So you just have to check the endpoints. So g prime here is actually -1, and that's never 0, and it's never undefined. So that means we just have to take g and plug in the 2 endpoints. And if we plug those in, we get 2, and then we get -2 here, respectively. Which means that if we take that 1 for x, and then we plug in 0 for y, it should spit out 2. And if we plug in 1 for x and 4 for y, we should get -2. All right, L2, this line here is harder, and that's going to have to wait till next class. So I would not touch the homework from this section yet. Well, you know what? I take that back. If you're going to look at the homework from this, I think the 3 through 13. Yeah, the 3 through 13 you should be able to do, because 3 through 13, well, 3 through 13 odd. None of those, all of those are just calculating D to find local max, local min, and saddles. So you should be able to do those. But anything after 13, 23 through 27 is this closed bounded set idea, and we haven't done those. Or we haven't really finished the problem yet. So, okay. This section is a little bit weird, especially this part we're about to cover. And I can tell you from the history of teaching this class, 11.8, usually people really have issues with. The next section after this one, the one that's Lagrange multipliers, this right here usually causes a lot of trouble. And then when we get here, people start to have a little bit of relief, at least for a little while. All right, everyone. A little bit, I'll say, you can go if you need to go. The mini exams and those things are going to start to become a little bit easier. Okay, so like the ones in the beginning were really like stretches, and the midterm was really, challenging you. But from here on out, the mini exams will be similar to the problems we're doing in class and similar to the problems you see on your homework. So they're not going to be like huge stretches where you have to like connect 3 or 4 different ideas together. Okay. And I'll send out a mini exam, sometime, hopefully by the end of the week. All right, everyone. Have a good day. I'll
Thank
hang
you.
out here for a minute if you have a question.
Thank you.